Welcome to the Explainer. So if you're building coding agents right now and you're sitting there wondering why your token costs are suddenly exploding or, why your agent totally loses the plot after reading just one single documentation page, well, you are definitely in the right place. Today, we're unpacking a masterclass in systems architecture from Dan Mercedes. We're going to look at exactly how to give your agents high-performance, rate-limit resilient web access entirely without bankrupting your context windows. Let's get right into the blueprint.
Okay, let's dive into this dramatic reality of token waste. When you point a coding agent at a simple docs page, it doesn't just, read the text. It swallows the entire raw HTML. I'm talking navigation bars, cookie banners, those annoying inline analytics scripts, the whole shebang. A single page can easily eat up over 9,500 tokens in raw HTML. But if you strip that down to clean markdown, it drops to just 1,678 tokens. That massive difference, that is pure, unadulterated boilerplate.
Think about that for a second. That is an 82% reduction in tokens. 82%. The default kind of lazy path of agent web access, where you just wire a basic fetch tool straight into your main context, leaves this massive efficiency completely on the table. You are literally paying frontier AI models just to read formatting tags. It's wild.
So, to fix this, we're going to walk through our battle-tested blueprint. We'll cover the context window crisis, the three axes of web access, the search and fetch stack, why thin CLIs actually beat MCPs, the sub-agent fetch pattern, and finally, the architect's blueprint itself.
Section 1. The context window crisis. Let's talk about the high stakes of taking that lazy path.
The core problem here actually isn't just the monetary cost, though that hurts. It's something called context rot. This is the silent killer of agent performance. It's kind of like trying to study for a test with a textbook where 80% of the words are just formatting tags. Just because a page technically fits into these massive modern context windows doesn't mean it's free. Your agent gets distracted, and its reasoning ability slowly degrades with every single piece of irrelevant code.
Actually, the lazy path compounds into three distinct failures. First up, context flood. A large page can easily be 25,000 input tokens, and it just stays resident there for the entire conversation. Second is cost. Because that context is resident, you're getting rebuilt for those exact same search results on every single subsequent turn. And third, rate limits. If you point a fan out of parallel agents at a metered API, you are going to hit 429 rate limit errors almost immediately. Total failure on all three fronts.
Moving right along to Section 2, the three axes of web access. Let's deconstruct this a bit. You see, web access isn't just one monolithic thing, it's really three distinct capabilities that require totally different tooling. First, you've got search, finding the actual URLs. Second, fetch, reading a specific page cleanly without drowning in code. And third, browser automation, genuinely interacting with a live app like clicking or scrolling. And this brilliantly illustrates why conflating these three is exactly how developers end up massively overpaying. You absolutely do not need a heavy headless browser just to read a static blog post, right? Name the access, then pick the cheapest tool for the job. Section 3, the search and fetch stack. Let's look at some specific cost-resilient tools. Here is the optimized stack recommended by our architect. For search, self-hosting just wins outright. A self-hosted search NG instance on a cheap VPS aggregates tons of search engines for literally zero cost per query, especially if you throw a Redis cache in front of it to absorb those rate limits. For fetch, you want extract first markdown. GeneraReader gives you super clean markdown for free at lower volumes, and Crawl for AI is just fantastic for bulk scraping. And finally, for browser automation, run a local instance of Playwright. It runs right on your machine, which means zero LLM cost. But hey, quick warning here. If you do go with hosted APIs, you've really got to beware of the fine print. Watch the rate caps, not just the marketing claims. Take Brave's API, for example. It offers 1,000 free queries a month. Sounds pretty great, right? But they cap that free tier at 1 query per second. The very instant you deploy a parallel search pattern for your agent, that 1 query limit shatters your entire stack. Always check the throttle limits. Section 4. Why thin CLIs beat MCPs. This is a crucial architectural debate. So I want to pose this structural question directly to you. Why does our architect argue that a thin command line interface fundamentally beats a model context protocol, or MCP server, when it comes to agent web tools? Well, it all comes down to how different agent harnesses handle context. Now, what's really interesting about this slide is the stark contrast in the resident memory tax. An MCP server actually costs context constantly. While some tools do defer loading schemas, others load every single MCP schema in full, every single session. You're constantly paying this expensive context tax just to have the tools sit there. A thin CLI, on the other hand, it costs absolutely zero resident context until the exact moment you call it via bash. It's stateless, it's cheap, and it keeps your context window completely pristine.
Now, to be fair, there is one very pragmatic exception to this rule: browser automation. Tools like Playwright drive a real, actual browser, which means they are inherently stateful. You have to maintain that session to click through pages or handle a login flow. So it doesn't really reduce cleanly to a stateless CLI. Because of that, Playwright stays as an MCP or an in-process library. But again, keep it running locally to avoid those crazy cloud LLM costs.
Section 5, the subagent fetch pattern. Let's look at the secret weapon for isolating raw data.
So, how do we guarantee that the main agent never gets flooded? Simple. We use a subagent. Here is the ingenious workflow. Step 1. The main agent delegates a URL down to a specialized subagent. Step 2. The subagent uses that fetch CLI we talked about to pull the clean, bounded markdown. Step 3. The subagent reads it, distills the content, and returns only the specific paragraph the main agent actually needs to know. The raw HTML, and honestly, even the clean markdown, never even lands in the parent conversation. It's brilliant. And the actual fetch CLI powering this whole subagent setup? It is literally just a 120-line script, absolutely packed with clever engineering. It's keyless by default, so zero setup. It carries a strict max tokens budget, meaning a runaway massive web page can't blow up your context. It outputs in structured JSON, which stops the agent from getting confused. And crucially, this is big, it uses a live browser user agent. A lot of basic Python scripts just get hit with 403 forbidden blocks. A live browser user agent bypasses those effortlessly.
Section 6, the architect's blueprint. Let's bring all these structural tools and patterns together.
So the crucial point is this foundational rule. Keep raw pages out of the main context by design. Everything else we've just discussed, the self-hosted search engines, the markdown extractors, the thin stateless CLIs, they are all just cost and rate limit optimizations built directly on top of this one core philosophy. Convert everything to markdown before the model even sees the page, and offload the actual heavy lifting of reading to a subagent.
Which leaves us with one final, pretty provocative question for your own codebase. Are you currently paying to put boilerplate into your model's attention? Let's be real, the lazy path is costing you 80% of your tokens, and pretty much guarantees you'll hit rate limits. The fix? It's literally just a day of plumbing and a 120-line script. Take this blueprint, go refactor your agent stacks, and watch your performance soar while your token costs absolutely plummet. Thanks so much for joining me on this explainer, and now, go build something great.